keeps on rising. But maybe just in the interest of everybody's schedule, I'll kick things off. So, welcome to everyone. As part of ARMA's hydraulic fracturing seminar series, we have today three icons, three of the most prominent geomechanics practitioners and specialists in the geomechanics community. And these three gentlemen will address the topic of stress calculations from logs, roughly right or precisely wrong. And this will be a 90-minute session. And the panelists for today are Professor Jon Olson, Dr. Alexei Savitski, and Professor Mark Zoback. And so we're going to give each panelist 20 minutes, up to 20 minutes, to express their position on this topic of long-standing interest. And then maybe we'll give each panelist the opportunity for a brief rebuttal, and then move on to questions. So as you watch this, please think of other topics along the same line where we could have some sort of a format where we can have positive debate and interaction. So we'll start off with Professor Olson. So Dr. Jon Olson holds the Cockerell Family Chair in Engineering number 17 at the University of Texas at Austin in the Hildebrand Department of Petroleum and Geoscience, or Geosystems Engineering. As we know, his research focuses on geomechanics and environmental impact issues related to hydraulic fracturing and unconventionals. Jon has 130 publications, and his honors include SPE Distinguished Membership. Prior to joining UT Austin, he worked at Mobil Oil's research lab in the 1990s. Now, Professor Olson's premise is that log-based stress estimation is a useful tool when applied appropriately. Dr. Olson.
Thanks, John. Let's see here.
John, if you can please hit the record button.
I think recording already started.
I think that's not our official recording. That's somebody's AI tool recording.
And I am too.
Are we ready?
Yes, sir.
Okay. So thank you for the invitation to participate in this debate with my esteemed colleagues, Alexei and Mark. And so I'm going to kind of set the basis for what I see as the technology of log-based stress estimation. And we'll probably hopefully set up the following two participants on their comments. So let's see here. Okay. So, we all have worked in trying to find stress estimates for many different things: wellbore stability, hydraulic fracture growth, reservoir geomechanics, other topics. Fault stability and reactivation is a hot topic now, and stress sensitive permeability. The comments I'm going to make are really all kind of focused on the hydraulic fracture growth aspects of generating stress profiles. And I really don't intend to cover things like poroelastic geospatial poroelastic changes due to depletion and injection, mechanical stress shadowing effects by hydraulic fracturing. This is all essentially coming up with a 1D interpretation of stress along a profile of a well. There's many different methods for assessing stress. I just want to list a few here: injection test, core-based methods, wellbore strain measurements and such, and log-based model-derived predictions. The log-based techniques have the advantage of continuous measurements across multiple zones. That's one of the big advantages, and I think is a reason why many people want to use log-based methods. The calculations are pretty straightforward, at least of the applications I'll show, just analytical equations that can be run through a spreadsheet. Not that logs aren't expensive, but compared to long-term studies and modeling, the method is fairly straightforward and affordable, let's call it. But I would argue it does require calibration data in order to be properly used. And that calibration data comes in the form of things like microfracts or defits to get frac closure. If you don't have that kind of stuff, there are some core test methods that have been used to estimate general magnitude of stress and other independent calculations when you really are ahead of the bit and can't do any better than that. Just briefly, this is not a complete list of things, but I just want to make sure to give credit to the many people that have worked on this topic before or through the years. And like for Price and Eaton did some early work that was used, often supporting drilling. Anderson and Newberry made some interesting additions, including the effects of pore pressure and microcracks was Newberry. McGarr kind of turned everything upside down and said the basic premise is faulty and proposed that initial stress state is what we call lithostatic, that all the stresses are the same at the end of the lithification series. Whitehead, Miller, Walls, and Dvorkin provided some interesting papers comparing model results to real data. And Pratt, Swarpinski, Sonne, and Zoback are a few examples of people trying to go beyond elasticity. And I think we'll probably hear more on that topic today, but I just thought these are some interesting papers that you might want to read if you're interested in the topic. So the assumptions, let me put together the assumptions for the elastic model as I see them. And I'm going to kind of describe the geologic history first and how we represent that, and then go on to some of the equations. But as sediment is deposited at the surface and buried, we all know this is a long-term process of compaction, cementation, and lithification. The mechanical properties of the rock are changing through time, typically becoming stronger and stiffer. Vertical load and temperature change are happening continuously as the rock is buried, as it increases with depth. Pore pressure changes will influence the stress state as governed by poroelasticity or other poromechanics. Doesn't have to be elastic based. And then there's a lot of horizontal action going on. Tectonics will, extend or contract the crust, and there's gravitational tectonics as well. The rock is deposited and lithified to present day configuration. Whoops, that's a mistake there. We'll come back to that line. The geologic complexity is idealized. So let me say that line that I just showed is what people often describe the log-based method as. Let me show how I would describe it. Geologic complexity is idealized into a simple model. The sediment is considered, the way I see it is sediment is considered elastic from the start with its present day properties. We include terms in the equations based on the derivation for gravitational loading, pore, pressure, and temperature. And we derive the equations with various boundary conditions representing horizontal tectonics. If we go back to this line that I thought that I deleted, one way this is described, this elastic model, is the rock is deposited and lithified to its present day configuration, and then gravity is turned on. And that's one of the premises for how these elastic equations are implemented. I like to think of it, it's still a significant simplification, but I like to think of it as we say that it's elastic from the start and we bury it, but we bury it not as a sediment, but as an elastic rock. But this initial state is one of the most, provides the most consternation for many practitioners. So let's just look at the elastic basis. I'm going to put some equations up here, but just for more of a visual effect and summary effect. But if you're interested in what the terms are, I've got a list of terms. I'm not going to enumerate those terms, but let's just look at the coordinate system here. Is Z is the depth direction, and X and Y are the two horizontal directions. We typically start with Hooke's law, and I'm presuming compression and contraction are positive. And the expression looks like this. So the strains in the three principal directions depend on the stresses in those directions times 1 over Young's modulus. And this is the thermal term with the thermal expansion coefficient times change in temperature. Bio's effective stress law is how we take into account the effects of pore pressure, and I'm using the capital S as total stress and sigma as effective stress. And that equation is written here where alpha P is the Bioelastic poroelastic constant, 1 minus the bulk modulus of the rock divided by the bulk modulus of the grain. This can sometimes be a challenging parameter to quantify, but it's a significant portion of the model. So once we get past the initial state, well, really this is setting up the model. We have to come up with some horizontal constraints to make a derivation. And so these are kind of three different premises that people use to come up with different models in the elastic world. So Eaton and others started out with what's called the bilateral constraint, which is both of the horizontal strains are equal to 0. The others have come up with a plane strain model. The ultimate equations that Tom Blanton and I came up with were presuming that there's only strain in one direction. And then there's also an unconstrained model basis, which neither of the horizontal strains are 0. So we take into account some sort of tectonics in both directions. If we look at the resulting equations, the horizontal stress is equal to this, if you're in the stress business, a very recognizable expression, Poisson's ratio over 1 minus Poisson's ratio times the vertical stress is the basic parameter that we operate off of. And then this is including the pore pressure term, which has the poroelastic constant times this Poisson's ratio term times the pore pressure. This bilateral constraint model, often you get stresses that are, some distance from the actual value you measure in the field. And so sometimes this is applied with a delta stress that you add, which is called the tectonic stress to calibrate it, so-called calibrate it to the right value. But that delta stress is added uniformly over the entire sequence, so it doesn't change the contrast and stress between sands and shales, for instance, if we're looking at that kind of fracture containment model. The plane strain model comes up with this equation. So I've highlighted in white is the same as the original bilateral constraint, but we have these extra terms here shaded in yellow, which depend on Young's modulus and some tectonic strain and the temperature effects. If we go to the unconstrained model, we just have a second term in that yellow area, which is the other lateral strain. And if we're trying to use this kind of model in a calibrated sense, you see both the bilateral constraint and the plane strain model have one unknown to solve for. That's the calibration term. And the unconstrained model has two unknowns. One thing also a drawback just philosophically in the bilateral constraint model is both of the horizontal stresses as derived are the same value. There is no stress anisotropy. The plane strain and the unconstrained model I haven't put on the slide for sake of brevity, but they both have equations for this horizontal stress in both directions. And depending on how you adjust the strain and do your modeling, the X direction may be SH min or the Y direction may be SH min, but just depends on how you go through the calibration process. But you do have stresses in both directions quantified for these second and third model. So let's talk about another difference between the plane strain model and that's what I'm really going to focus on for the rest of the talk, the plane strain model, but how it's different than the bilateral constraint. For calibration for the plane strain model, we use a strain term, the bilateral constraint or other, there's many different iterations of this, but adds a tectonic stress. So let's look at if we have a stack of 3 layers, shale, sand, shale, which is often conventional oil and gas hydraulic fracturing situation. We have let's presume that the shale modulus is less than the sand modulus, and if we add a fixed strain uniform over depth, we basically shorten the whole sequence, and the change in stress for each layer is variable based on modulus. If we go over here and we add a delta stress to the model, we get this displacement discontinuity from layer to layer, which is a non-physical result. Okay, so the change in strain that is a function of the mechanical properties, and this it doesn't seem like a internally consistent model, so we don't recommend doing things that way. So we have this final result, which looks like this from Blanton and Olson, the Poisson's ratio term, the pore pressure term, a calibration term, which is tectonic strain, and thermal term. And we have that one unknown that can be solved by getting one calibration measurement in the field. Okay, so let's just talk about a little bit of data. I think I've got about maybe five or 6 minutes left here. So there's a lot of data that shows that stress levels in fracturing stress varies with pore pressure. This is a depletion path in the North Sea. Depletion decreases frac gradient. If we inject, that increases frac gradient. That's pretty well established from data in the field, and people understand that pretty well. But this SH min changes as a fraction of pore pressure, and this delta S sub H over delta pore pressure of 0.71 from the North Sea can be likened to the pore pressure term in the elastic model. And this constant, which is pore elastic constant times the Poisson's ratio term, is some fraction less than 1. So the main case in the Blanton and Olson paper, where we tried to show that show some constraints on whether we match the data, was a data set from a GRI well in the Canyon Sands in the Sonora field. And this is in situ stress, SH min on the y-axis and depth on the x-axis, a series of siltstone, sandstone, and shale. The black diamonds are all the calibration tests that were measured in the GRI experiment. We use one calibration point for both models, and this is the plane strain model and the bilateral constraint model. We matched that value by adjusting the strain for the plane strain model or adjusting the tectonic stress addition for the bilateral constraint model. And you see that for the sandstones, both models are reasonably accurate and have a similar fit. But for the shales in between them, just having this one calibration point, the delta stress between sand and shale is very different. So for the plane strain model, based on the Blanton and Olson equations, we get about an 800 psi difference between sand and shale, which would help you predict your frac height barrier. The bilateral constraint model with the delta stress has about 1500 psi, significantly different. If you look at the data here, that the answer based on the measurements was about in the 800, 850 range. So for this particular example, our plane strain calibrated model got good match for every layer in the sequence, and actually seemed to do a much better job of predicting the delta stress into the shales than using a stress calibration point. I'm going to skip this slide just for the sake of time, but in the paper you'll see we do some statistical analysis of the range of the fit using all the calibration data. I do want to show just real quick what kind of rock are we talking about. So if we look at the sand that's in this location right here, we have this core at UT actually. As you can see, it's a pretty clean sandstone in much of the zone, but there's some conglomeratic effects at the bottom. That's my 17-minute warning there. And so then the shale is actually quite massive. So it's a very interesting sequence, and I think that's worth thinking about, that this is not a... further up in the section is turbiditic sandstones with quite a bit of variability. One other case I'll show you is the case of Lost Hills diatomite that Tom and I worked on. And we have the properties here: Poisson's ratio, Young's modulus, and density. I'm not going to dwell on the values there because of the sake of time, but for this particular example, we had 20 different RFT measurements throughout the sequence, so we felt like we had a pretty good handle on pore pressure versus depth. Notice this is a very shallow well from 1700 to 2600 here, and our stress measurements using this plane strain model gave the following profile. There's the vertical stress. Vertical stress based on density, SH min based on our model, and SH max based on our model. The interesting thing to look at here is the predictions of stress regimes. So at the top of the log, we were predicting that the minimum stress was equal to or greater than the vertical stress also at the bottom of the log. That was consistent with tilt meter observations where we're getting evidence of horizontal fracturing above and down here below the main pay section. Normal faulting stress regime in the pay zones that were fracking, and then 200 to 400 psi stress barriers where we definitely thought we saw containment. Now this is a lot of detail, and this comes back to the roughly right or precisely wrong. I'm not trying to pretend like all of this is precisely right, but it does bring up a lot of interesting, having this equation and being able to quantify both horizontal stresses brings up some interesting things about whether your stress regime is changing and you're transitioning between horizontal and vertical fracs for an application like this. The last case I have is a Barnett Shale case, and I'm going to skip to the stress profile here just to say for this particular case, I just pulled this the log data out of the literature, and I didn't really have any calibration data, so I used a critically stressed faulting theory just to show that even if you don't have any information, you can approximate a calibration point. And so I basically came up with a 0.6 psi per foot frac gradient for the main pay zone of the Barnett Shale, and you can see using that, and this is not constrained at all, but it does show even with that limited information, I could come up with some estimate of the stress barrier as well as the stress anisotropy values. So strengths of the log-based method, I would say, or is it's a useful estimation over which you can have continuous coverage. Mechanical properties for a successful model need to be readily quantifiable, and elasticity certainly makes that possible. May not be precisely right, but is certainly simple and useful. Static dynamic correction for the elastic properties from the log can be a challenge sometimes, but we have methods to take care of that. You can compute it on a spreadsheet. Those of you who still use spreadsheets, this is an advantage, makes for quick calculations. And corroborating data from various rock sequences, I showed you some quick examples here, suggests that we can get reasonable results, and we get both of the horizontal stress estimates. Although really in my application, I've only really ever used SHMIN. Limitations and drawbacks are the potential implausibility of the initial stress state, how we are modeling the geology prior to lithification, and lack of accounting for, and this kind of is the same topic, lack of accounting for the non-elastic time-dependent relaxation of rock. So I put this geothermal in here for John to make a shout out to geothermal. I mean, calculating stress from a log in geothermal, I think, is perhaps a task for another century. But anyway, so that's the way I see this. So I would argue that we're roughly right in what we do when we do this log-based method.
Thank you, John. We'll circle back to you after the other two speakers. So our next panelist is Dr. Alexei Savitski. And Alexei is a Geomechanics Advisor in the Argentina shale asset and an SME for in situ stress characterization and near wellbore fracturing processes at Shell. And he has more than 20 years of experience in petroleum geomechanics and 15 years specifically in unconventionals. So his current focus is on the problems of casing deformation, interwellbore communication, and integrated diagnostics. He is also vice chair of the Hydraulic Fracturing Technical Committee for ARMA, the American Rock Mechanics Association. So Dr. Savitski will review the assumptions and applicability to hydraulic fracturing of log-derived stress calculations. Alexei.
Thank you, John. That's a very kind introduction. And I'm really honored and pleased to debate this question with my co-panelist, Jon Olson and Mark Zoback, and the rest of the audience, online audience. We have more than 200 people now. Give me just a second, so I'll share. Please confirm that you can see it.
Yep.
Thank you. And I'd like to start with a couple of disclaimers. First is I'm coming from a practical side, so I'm representing practitioners here, and I'm more than interested to have a roughly right solution for this problem of defining stress profile for applications with mostly focus on hydraulic fracturing, but also as applications in petroleum or subsurface geomechanics. But today I will be taking an opposite position and making a case that quite often, probably even more often than we know, stress profiles that are being calculated from logs, specifically from Eaton, but not necessarily. And in those cases, they would be quite often wrong, sometimes spectacularly so. What Jon just presented before is, in my view, is a very thorough and state-of-the-art approach using this standard technique. Every practitioner is doing it, so that's a typical core skill for 1D mechanical earth model building. And I still have significant issues with the process and some of the assumptions, like, for example, dynamic static correction, which I will discuss today. My second disclaimer is being in an informal discussion, so I decided to do it as sharing my thoughts and doubts, not on behalf of company, so I'm not representing a view of a geomechanics community or discipline at Shell. This is really my views on this. I didn't have a chance to discuss it with such an experienced audience like we have right now online, or such deep experts in this subject as Jon and Mark, other co-panelists here. So let me start with sharing my thoughts on this subject. And I'd like to start with a picture from Blanton and Olson, so it's Jon's paper, 25 years ago, or 26. I think it's so old that I used this movie trick by coloring it, all black and white movies, right? And I just color it data points which correspond to actual stress measurements, so you can see them better. But this is, I'm not really much interested right now in this case study and whether it's right or wrong. I'm using it to illustrate concept. Although this is, I think, a very nice calibration of data. What is important, it has all the elements I need for discussion. So it has overburden gradient here, shown this straight line. And then a couple of versions, scenarios of calculating minimum horizontal stress using conventional model, and then improvement that was presented in the paper. You can take eyes of this. And then a few data points of actual measurements. What is important is that in stress profile calculations, there is always baseline gradient. If you're in deep wells, 10,000 feet, 3,000 kilometers in many applications, then it does make big difference for practitioners to know, are you in an environment where your minimum horizontal stress is 0.7 psi per foot or 0.9? Is it overpressured formation? Or, and that gives you a basic idea of how overpressured, overstress this formation is. But then there are a lot of local variations that you can see here. So it's an excellent example of that, which happens on the scale of at least 10 feet. But you can always get even higher resolution, which is constrained only by log resolution. It would result in practical issues of how to do upscaling of high frequency data, which often is done ad hoc, but that would be outside of scope of this presentation. So I'm just looking at the physical assumptions and justification for some of the steps in the process. So in this introduction, so I'll focus, like Jon did, on in situ stresses. So I'm not looking at stress being induced by operations, injection, depletion, heating. It's what it is there before we do anything. Then I'll carry forward this concept that we have a baseline gradients and then local variations, which are mostly driven by lithological variations informations. And that's what equations, whether it's elastic or inelastic, are trying to account for. And then it's also important to recognize that it was already discussed by Jon Olson before me, that the quality of interpretation is needs to match our end use for the data. And there are many, so I'm missing maybe a few of them, like fault reactivation assessments, but it's mostly used in drilling operations, wellbore stability or fracture gradient to prevent fluid losses. It is being used in many injection projects, thermal, steam injection, CO2 sequestration, water disposable projects. In complex 3D geomechanical modeling, where there is a structure in the field and field scale modeling is required, typical application would be a 4D seismic or complex reservoir engineering, where stress-dependent permeability plays a big role. But I think that one of the most sensitive application for vertical stress profile, 1D vertical stress profile, is hydraulic fracturing, and especially in shales, where the changes are subtle, so lithological units are more difficult to define as compared to conventional applications where you have a pronounced sand shale sequence. We face several challenges here. So many people are doing it as their day-to-day job to create this type of profiles, and many people have discovered that if you just calculate stress profile from using equation from first principles, they can log as input vertical stress and pore pressure as measured input, and then they're not predictive most of the time. And the robust process, as was just explained, would include calibration to actual field data, which could be stress measurements, microfrag, sometimes minifrag, extended leak-off tests, or it could be observations. So maybe we don't have stress tests, but we have hydraulic fracture operations, and we can use ISIP as a constraint. So it's not exactly measurement of stress, but a good constraint on it. So some type of field data would be required to calibrate the workload, because even when we believe that the workload would give us reasonable results, we wouldn't trust it unless it's calibrated to the field data. So it's not predictive from the first principles. Then when we calibrate it, let's say we have data, what do we calibrate? Do we calibrate the base, the gradient, or local variations? So for hydraulic fracture modeling, this height grows in a complex variable layered environment. It's these high frequency variations which are very important. But do we actually calibrate to them? So this model, and again, I should say that I'm not discussing the case study, so I don't know whether it's right or wrong, and I don't know the details, but it's an excellent illustration that, let's say you have a case like that, and then you have calculated stresses, and then you have actual measurements shown in red, and you're calibrating, and this looks like a great calibration, so this profile is justified. I've seen many times that people claim it's calibrated. And then, well, what if it's like that? This matches data as well, and actually it's much simpler. So do we calibrate high frequency with depth of variation of stress profile when we have only one or very limited number of measurements? I'm not sure. So are you sure? So when you're doing this, so I think this question that you need to be asking, is your calibration to actual test, is calibration for the ballpark number, for the baseline, or for actual variations? Then, as I said, hydraulic fracturing is very sensitive to stress profile, at least based on theory that we are using for simulating hydraulic fractures. And oftentimes, models would predict fractures which are too small or too large compared to actual observations. Observation can be on frac heats, interwellbore communication, some diagnostics, sometimes pressure, sometimes microseismic, although it's a different source of uncertainty, not only source of information. And if our model fractures are too big for the model, then, and we are trying to constrain it, it's not necessarily stress. So quite often people would say, okay, model fracture is too big. We have data that it's much smaller. Maybe you have radioactive tag in a vertical well, so you know it's much shorter. And then it can be strengths. Maybe there are some strong layers which prevent fracture propagating. Maybe there is a T-shape geometry which prevents fracture growing. But maybe it's stress. On the other hand, when model fracture is too small and actual fracture is much bigger, then sometimes there is nothing else left but to say that fracture gradient is completely wrong. And good example, I think, is HFTS2. Because until we, and this is a pilot for those who don't know, in PERM, and it's a public-private partnership, so a lot of data are public. And I'm referring to paper for those who are not familiar with the details. But what you see here in the central panel is data from distributed strains sensing of vertical pilot hole in the middle of pad where multiple horizontal fractures were stimulated, and the well is landed at this depth. And this, you can see this blue-red dipole signal envelope, and that was shown to very closely match the top edge or bottom edge of fracture in a stage. So essentially, we know how tall is our fracture, and this would be the fracture height at each point in time. Time is a horizontal axis here. And this is accompanied by microseismic data set. So when we used, from first principles, calculated anisotropic model, and isotropic actually was even worse, two models of our stress profile based on logs, and then you see there is some variation in stresses local. This is zoom out model, but if you zoom in, so there is a step here. And those initial models, they wouldn't predict this spectacular fracture growth, which is 1,800 feet here, but there are more data from Permian showing that there are some water cuts in Avalon wells 3,000 feet away above Wolfcamp development wells. So we're talking about fractures in the order of 2,000-3,000 feet, where every model before that was assuming fractures 300 feet at most, consistent with microseismic. So in order to get this high fracture growth, we have to change stress profile. Now we cannot do anything with strength because strength is already brought almost to zero to trying to match this data. So that's, for me, is an example of being precisely wrong when it can be demonstrated. Data like this are not only useful because they give you final fracture geometry, they also give you fracture geometry evolution with time. So the same panel is now shown here at the bottom, where again time is horizontal axis, and then depth is vertical, and then color represents this strain, and blue over red or red over blue are top and bottom edge of the fracture. And now microseismic starts to make sense because you can see microseismic being completely within this envelope, and the envelope of microseismic is tracking the edge of the fracture very nicely. So you can see here the shallowest points, this point, this point, this point of microseismic. So I assume this point corresponds to this one. And they're perfectly matching on depth and on time our strain measurements. So we do think it's real fracture, it's real in time, and it can be used to calibrate our stress profile, which was initially precisely wrong. Let's get to Eaton equation. And I will be using very simplest form of equation. So I'll talk a little bit about extensions, but I would like to demonstrate my problems with workflow using its simplest form. As was just explained, so I'm not going to repeat all the equations, but it relates our horizontal stress to external load, which is gravity, which comes here through vertical stress, but also loading through pore pressure. And we assume that we know our vertical stress through density log integration, and also we know our pore pressure through independent measurements. So what's left here is Poisson ratio, BO alpha. Quite often practitioners even wouldn't use BO alpha here as a parameter, they would assume 1. What is important is that in our stress calculations, there is a loading component, and that could be not only gravity, it could be also tectonic stress, it could be temperature, and of course pore pressure. And then there are rock properties. And here in this Eaton's family of equations or workflows, rock properties are assumed to be elastic, so we're modeling it as elasticity. And when predictions don't match observations, then we have to do something. And this equation doesn't have much flexibility. You cannot quite match actual data if you offset by 1,000 psi. So there are multiple variations of how you can make it more physical by bringing in a stress or a strain tectonic term, and that's the best way to shift the whole baseline because it's additive term. But also in order to get different variations on a small scale, high frequency variations, then anisotropic models, VTI models, create significant difference, and it can be shown here. You can see on this second track from the right, black line is isotropic stress calculations similar to this model. shown at the top. But red one is using anisotropic equations, which has a little bit extra term, and then a ratio of vertical and horizontal Young's modulus. So all it can be done, but it results in a drastically different profile. So we have difference of about 0.2 psi per foot between two calculations. That's very significant. But all this can be done to match actual data, and the question is, what's left? So do we really need just field data to get an idea of our stress profile? What is the predictive power of our calculations if it's wrong until you really calibrate everything with the field data and you still have remaining uncertainty? Let's look quickly at what can be right or wrong with this equation is from the point of view of elasticity. And I think one of the obvious things that many people recognize is that elastic linear, especially linear elastic loading, doesn't really represent, it cannot represent the stress path and deformation history of rock sample at depth through geological history, getting from surface to deep location. And what we are doing here is, I think, good analog would be, if you want to measure the height of a hill or mountain, so do you really need to measure your inclination and every turn and incremental change in height along the long and winding road? Or there are some other ways when you're at the top of the hill and you can just measure drop the rope, or use a ruler and just measure how high it is. This analogy is bringing me to discussion of when do rock actually deform elastically? And to illustrate it, I'm using triaxial tests. It's not our uniaxial assumption in Eaton's equation. It's just example of triaxial test. And in triaxial tests, quite often, not always, but quite often, Foxwoods interpret linear slope on a primary loading curve as a linear elasticity, and then you increase the load, and then you the toric load, and then it starts to behave inelastically, and then at some point it would break. But that's not an elastic slope. We know this, right? Because it's not recoverable, it's not reversible. It's a plastic deformation. It's linear, but it's not elastic. And then in a good test, you would find unloading, reloading loops. They're consistent. They have much steeper slope. So which one would we use for dynamic to static correction? I would argue that it's red lines which would give us elastic properties, not green ones. In your process, when you do it at your workplace, are you using green or red? I've seen actually more often that people would use pseudo-elastic properties interpreted from this linear slope, which is green. And then there is an inconsistency because we're looking at the problem from a linear elastic point of view, but we are not using elastic parameters in the calculations in the dynamic to static correction. So that's something that I'd like to debate with panelists and the audience later. But if you use these red lines, the point is that Eaton equation starts to have physical meaning to me when I think about it not as a representation of loading history of sample, but as an unloading experiment. And let's make a quick thought experiment here. There is no tectonic loading. We're just looking at gravity, and it's a uniaxial strain unloading process. We take a core somewhere at depth, we constrain it in a barrel. We don't allow it to expand, so there is zero strain and horizontal strain. And we bring it to the surface. We remove our vertical stress sigma v. Think about it, the sample is sitting somewhere here on a pressure depth curve. So this is depth, this is stress, this is vertical stress, pore pressure, and this is our minimum horizontal stress, smaller than vertical. And we bring it to the surface. We bring it, and like on the previous slide, I'm saying, it's elastic unloading process. So you roughly end up somewhere. You wouldn't get to zero stress. There is something still there, residual. And that residual is lithology dependent. It will be different from sandstones. It will be different depending on the clay content. And I think that Professor Zoback will be talking more about viscoelastic relaxation in the next talk. I think that's what it depends on. You can take the same cartoon, and these are all cartoons. I'm just trying to convey you basic ideas. Don't take it as a theory, please. And same thing, so we're looking at now on a just slightly different plot of horizontal versus vertical stresses. We'll load it to the depth. and then let allow for some creep and sample with time. So we'll have increase in horizontal stress depending on how what is the creep rate of particular rock type. And then if you wait long enough, so you can get to this lithological equal stress state. That's exactly what was shown. And some people argued before that it should happen with time. And then what's next? Let's do the same thought experiment. We'll bring this sample in a core barrel to the surface. We remove vertical stress, and we would still have some residual stress, right? What if we applied, and we, as I said, in this thought experiment, there is no tectonic stress, so we cannot blame mismatch on tectonics. There is only, it's a just relaxed basin. And then what would be the meaning of this Poisson ratio? So if you were trying to relate horizontal stress through this dashed green line, well, I think that there is no physical meaning. If you try to get data from the lab, whether you use primary loading curve or unloading curves, you wouldn't get here. This is, it's just coefficient. And that give me pause with using dynamic to static corrections, trying to use this type of green equation, which I think is inapplicable to what we are trying to do here. To conclude, I think that with physically measured meaningful Poisson ratio, an equation as is not correct. We would be missing residual stresses even when you have no tectonics. We can add tectonics, which may be real, maybe not. In some places there is tectonics, and I'd like to discuss it with panelists and the rest of the audience. But you can compensate for it, but it's still we're still missing variation due to relaxation on top of that in the Eaton's approach. You could revive Eaton type of approach if you think about it as a primary elastic unloading, which I think is a correct physical assumption. However, it would add to the equation some sort of residual term, which we don't know. Maybe it's possible to calibrate it with actual rock physics data, such as TOC, it's a total organic content, if it's source rock, or clay content, or porosity, or some other lithological characteristics. Maybe it's possible, so I haven't seen this being done. It should be, but it should be specific to each facies in our rock. And of course, these type of equations can be generalized for accounting tectonics or anisotropic behavior or thermal effects. So this is just the simplest form just to convey you the concept. So my conclusion is that I'd love to have log-based, reliable log-based stress estimate. It's absolutely needed. I'm afraid that we are doing it because we can and we don't have any alternative to do it. But I think that quite often it's precisely wrong rather than roughly right. And there are some examples of that. And in many other cases, we just don't know because we don't have data to prove that it's wrong. I rest my case here.
Thank you, Alexei. Our next and final panelist is Dr. Mark Zoback. Professor Zoback is the Benjamin M. Page Professor of Geophysics Emeritus at Stanford University. And Dr. Zoback, as we know, has received a number of honors, including election to the U.S. National Academy of Engineering. He's written 2 books on reservoir geomechanics, has 250 peer-reviewed publications, and 5 patents. He's currently working on issues related to large-scale CO2 sequestration, induced seismicity, and optimizing production from unconventional oil and gas reservoirs. And Dr. Zoback will describe using viscoelastic stress relaxation to explain and predict layer-to-layer stress variations with depth in sedimentary basins. Dr. Zoback.
Thank you, John. And I'd like to also thank both John and Alexei for their excellent presentations and sort of setting the stage for what I want to talk about today. I don't care about winning this debate or any other. I really do care about getting the stress right. And those of you who know me know I'm a very practical person. And we're, thinking about optimizing hydraulic fracturing today, but wellbore stability, of course, requires precise knowledge of both principal stresses. And induced seismicity requires knowing something about the reference state and stress orientation and relative magnitude. And we spent 40 years, publishing ever improving stress maps to accomplish that. But let's focus on getting the stress right. And I have a long list of people to thank for their help over several decades. Work on viscoplastic deformation of rock started with Carl Chang and Paul Hagen on unconsolidated, poorly cemented sediments. The modern work I'm mostly going to be referring to today started with Hiroki Sone's remarkable work in the lab and wound up with the work that Ankush Singh, here he is, the modeling he's developed to make this a practical technique for developing continuous stress profiles. And I have a lot to owe to all of these individuals. Elastic loading models has been discussed, and incorporation of various parameters. This is the BTI version. And, as, a fundamental point, and we're going to focus on normal faulting to keep it simple. SH-min can be easily measured. SH-min magnitude and orientation control hydraulic fracture growth. So we'll just, work on that. And in these kinds of equations, the minimum horizontal stress goes up as rocks are stiffer. Now, I'm, familiar with discussing this, and I've previously commented in my short course. And you could argue that I get overly animated when I'm talking about the limitations of these models, but I'll try to keep it constrained for right now. So what is the right way to think about this? I think it's really pretty simple. You start with the idea that stiff rocks are going to be in frictional equilibrium. We all learned this equation from Jaeger and Cook, probably. And this place, in the case of normal faulting, it places a bound on the lower limit of SH-min. Okay, SH-min can't be too low because of normal faults would be activated. But rocks aren't all stiff, and when they start to become viscoplastically, and this is what I'll show you for work on unconventional reservoirs, we were able to derive a constitutive law and then a methodology that is applicable to these kinds of rocks in a practical way. And the key thing here is that SH-min goes down as the Young's modulus increases. Because the way, if this goes up, the only way this can go up is for SH-min to go down. Okay, and so, and also as in viscoplastic rocks, this N parameter, the viscoplastic coefficient is higher. I'll show you that. Now, there's a special case in which normal faulting, and hydrostatic pore pressure are defining the environment. And then, the simple Eaton equation seems to work if, pore pressure is hydrostatic, Poisson's ratio is about a quarter. We get, this ratio of, 3 to 1 for the maximum to minimum effective stress. And from this equation, if mu is 0.6 and we have hydrostatic pore pressure, you get almost the same thing. And so you can see how Eaton, when he points this out, that, when in the Gulf of Mexico, when pore pressure was hydrostatic, his proposed method seemed to work, but it was only at greater depth that things became more problematic. Now, getting the stress right, I believe, for the purpose of this conversation, comes down to assuming frictional equilibrium in relatively brittle rocks. I'll show you lots of examples of that. And then, so the reference state, which Jon referred to it in his presentation as being sort of an isotropic state as proposed by ARMA, I actually think the reference state is frictional equilibrium. And then for the rocks that are not brittle, I want to introduce the idea of viscoplastic stress relaxation. I want to apply it to observed stress variations with depth. And then I want to use it in the few cases where we've had the opportunity to make useful predictions. So in my first book, I went through many examples in which frictional equilibrium, really describes the stress state. This is the Travis Peak Formation. The measured stress versus the predicted stress is fit very well. These are all cases where we know the pore pressure, the stress path in Valhall, subhydrostatic pressure here. South Eugene Island in the Gulf of Mexico, the limit seems to be the frictional resistance, frictional equilibrium, and so on. Now, the reasons for this are, beyond the scope of this presentation, but I do think it's the right reference state. And I think where we see deviations, where the measured stress is greater, is due to, processes such as viscoplastic stress relaxation, as Alexei just alluded to. So, the modern work we've done was led by Hiroki, and we did a lot of experiments under different kinds of conditions. We developed constitutive laws based on, first we were working with 3-hour data, then 2-week data. We eventually went out, I think we did an experiment for a month, and we developed this power law. Now, we found that this power law worked very well, and it had been used before to describe how cement works and other rock-like entities. So this is the creep compliance. It's the strain normalized by the applied stress. B is just 1 over the Young's modulus, and N is this power law exponent. And by plotting the data in log-log space, the slope gives us N, and the intercept gives us Young's modulus. Now, if we look at real rocks, we can see here the barnett is not very creepy when applied, when a constant stress is applied. But as you increase the clay, it becomes more creepy. Haynesville is a much more creepy rock, but again, as we add more clay plus TOC, it becomes much more creepy. Now, in laboratory space, we apply constant stress and we measure a time-dependent strain. In actuality, if you had kind of more or less a constant strain, you'd see an immediate, you'd see immediate elastic stress, and that viscoplastic strain would relax. And we're using viscoelastic theory for reasons which we documented very well in one of the early Sony and Zoback papers. Now, in practice, if we had, clay-rich shales and sands in frictional equilibrium, what this would mean is that in the shales, the stresses would be higher because viscoplastic stress relaxation makes SH min increase toward SV. Okay, so you have higher stresses than you would anticipate, and of course, in classical hydraulic fracturing, this is just what you hope for, so that you have fracture containment in the sands. And as we apply the constitutive law we developed to normal faulting, it has a simpler form, and this is kind of the form we work with. And it's actually, we do require calibration, but it's a much simpler process, as I'll show you. Now, Xiaodong Ma did some really nice work to demonstrate that, when we're talking about rocks with, very low N, pretty stiff rocks, we have very little viscoplastic stress relaxation, even over very long geologic times. And, those are the cases in which we're assuming we can use, frictional equilibrium. We just realized I published the first stress polygon 40 years ago, which means some of you are getting old. But we're usually at the periphery, which is the surprise. We could be anywhere inside, of course, the polygon, but we often find that we're at the periphery. Because there's, brittle frictional equilibrium is active. And when we have viscoplastic stress relaxation, that's not the case. In other words, these rocks with high N are the ones that are going to be relaxing over geologic time. Notice that most of the relaxation occurs in, about 1 million years or even less. It's a fast process. Now, let's start with some qualitative examples. HFTS1, a paper by Arjun Kohli and I. We took all the defits in the mini fracs, in the horizontals and in this near vertical well, this near vertical well, and we plot them here. This is just the data, And what you can see is it's very appears to be very complicated. Low stress, high stress, low stress, high stress, high stress, low stress, high stress. It seems rather chaotic, but large scale variations, on the order of 10 megapascals, 1500 psi. Now, what Arjun and I did is we said, okay, suppose this concept is right, then the low clay plus TOC areas should be sort of in frictional equilibrium, and we should have low stress. And the high clay plus TOC areas, should have high stress. And, here in the low stress zones, we're sort of in normal faulting failure equilibrium. And in the high stress zones, we're not. The Moore circle is much too small for. And, even in this kind of simple qualitative way, Arjun and I kind of go through the mini-frac data showing, well, here, when you start pumping frac stage, you get microseismic events immediately. Here, when you start pumping, you've got to build up the pressure quite a bit until you start getting microseismic events. And where we had focal mechanisms available to us, you can actually walk through each of the focal mechanisms as pore pressure was steadily increasing and explain the slip. So these variations are real. They cause a lot of the patterns in microseismic data that seem sort of inexplicable, but they're just reflecting the variations of SH-min with depth as measured here. Now, Xiaodong Ma and I looked at a couple of horizontal wells in the Woodford Formation in Oklahoma, and the measured shut-in pressures from the various stages are showing a strong variation in stress magnitude. And if that's all you were looking at, it would look pretty chaotic along the length of the well. But we made the point that these wells have kind of unusual trajectories. It looks like a roller coaster ride here, but it's a 4,000-foot well, and these are only several tens of feet. The problem is the Woodford has got distinct lithofacies with different amounts of clay plus TOC. And here, what you can see is the stress is varying, with the clay plus TOC. And it's not a perfect fit, but, overall, it fits pretty well. Here in this other well, it's exactly the same thing. As clay plus TOC vary, so does the stress magnitude. And in the high clay areas, higher clay areas, where, SH-min is closer to the vertical stress, as we would expect. So now let's talk about predicting stress. Well, what Xiaodong and I did, we looked at it a couple different ways. We made a correlation between SH-min and clay plus TOC in these wells. That worked pretty well. And here we're actually using the viscoplastic theory, using an empirical correlation between measured Young's modulus and N in the lab. And what that does for us, it gives us a prediction, the black line here, which is good. Roughly right, but not precisely right. We underpredict the stress in a couple places. The upper bound, based on the uncertainties in this correlation, seem pretty reasonable. The lower bound is irrelevant because the frictional limit is a physical lower bound, so you really never get below that. Now, the work Ankush did as part of his thesis is really kind of where we are today. And this is from the Midland Basin, not that far from HFTS1. And if you look at the available direct measurements of SH-min, there's just a whole lot of scatter. And these lines are 1,000 psi apart, and so you see about 1,500, as much as 1,500 psi or so of scatter. And so, is that, what is the least principal stress? And when you have a single measurement, is that measurement valid? And what Ankush was able to demonstrate by some very clever methodologies that he developed was we could fit these data very well. And so the green is the prediction. It's kind of hard to see here, but when you blow it up, you can see the predictions are really quite good. And even down to this single measurement and the climb. And when you focus here in the middle Wolfcamp, you see the predicted stresses are quite good. So, this is an unusually complete data set, right? We almost never have data that's this good. but it was, great for us to test the viscoplastic stress relaxation idea and to compare the predicted stresses to elastic loading models. The parameterization is important, and it's all described in the paper. Then Ankush used some machine learning methods for the solution. And then we did a number of statistical tests. In other words, use half of the data, predict the other half, omit data using, kind of the bootstrapping technique, and to try to predict the data. So we spent a lot of time in this paper demonstrating we just weren't overfitting the data because we had so many measurements. We could actually, it actually had predictive capabilities. This figure in the paper showed that, while we probably would like to have E horizontal, if you have E vertical as measured from logs in a vertical well, it worked out just as well. The way to think about this is the ratio between E horizontal and E vertical just turns out to be another parameter in the parameterization. And we tried to make the model work. If it fits here, but it doesn't fit very well at the other depths. This is work of Kevin McCormack in the Denver Basin. The prediction is over here. It fits the defits, very well. It kind of explains what we were trying to understand in terms of vertical fracture growth. But if he tried to pin the Eaton model to these calibration points, the green and the black are significantly different. If you use this data point for calibration, it was way off. And so again, the VSR model seems to be working well. Ankush has recently taken a shot at modeling the stress variations at HFTS1. And of course, we have a lot of data here, so you could argue that the value of all of this is less, but we're still making predictions in areas where there are data gaps that are really important with respect to hydraulic fracturing. And that was the point of a paper we put together 2 years ago for ERTEC to demonstrate these are two real stages. And the colored here is the Coley and Zoback blocked stress diagram, and a fracket at level A and a fracket at level B were modeled as best we could. And yet, you get very distinctly different fracture geometries, the fractures following the stress field. And, this is really important. Yeah, we gotta, this is a completely hypothetical case, but these were real cases. And of course, there's nice containment here when you have higher stress above and below. In terms of HFTS2, which Alexei mentioned, the stress profile we use predicts strong upward propagation. The fiber data kind of confirm that. But if you were just thinking, at least that SH-min was going to be following Young's modulus, there's a strong increase in Young's modulus here at shallow depth, which would have predicted a much higher stress and a stress barrier, a frac barrier, excuse me, and whereas using frictional equilibrium as a reference was more, consistent with what is observed. I literally woke up in the middle of the night thinking about this data, and my wife's response was, get a life. This is data from the 1980s from the multi-well experiment, and Phil Nelson, who was interested in this increase in pore pressure at depth, summarized the data from a lot of other papers in a convenient way. And so we used Phil's summary. And the key thing here is, the minimum stress is increasing, more or less as predicted from the pore pressure increase and the vertical stress. But all the muddy rocks, the mudstones and the shales, almost all of them showed the least principal stress to be equal to the vertical stress. In other words, essentially near complete stress relaxation. In other words, SH-min becomes equal to SV. And there were a couple of cases like that we observed here in the Woodford data. And finally, what we find that due to the porpoising of wells, this is from the Marcellus work from Gator Alali and myself, we found that when we were up here in the Cherry Valley, The minimum stress, which is the red dot, is below the vertical stress, so you'd expect vertical hydraulic fractures. And yet down here in the lower Marcellus, the minimum stress is essentially equal to the vertical stress. The red dots are equal to the dashed line, in which case the stress is not controlling the hydraulic fracture, and you'd expect then the hydraulic fracture to follow, say, weak bedding planes. And of course, a couple weeks ago, Egor Dontsov gave a very nice example of this using modeling, and how, along the length of a lateral, when they're changing, the lithofacies that they're in, one could actually get, horizontal hydraulic fractures for some stages and vertical hydraulic fractures for others. So I think it's, sort of frictional equilibrium as our reference state, and then deviations from that state are caused by this relaxation process. It helps us understand observations, and we have, much better observations than we've ever had before, and it helps us make useful predictions. So just to conclude, I think these can be approximately right, but I'm afraid, John, it's 2 against 1. I think elastic loading models are always precisely wrong. I've not tried to do, my arguments differ somewhat from Alexei, although there were certainly points of commonness. My problem are, I think the geologic assumptions are unreasonable. And until we had this VSR technique in a quantifiable way and a way to apply it to real data, we really had nothing to offer to provide, to really systematically make continuous stress profiles. But I think we do now, and there's a lot more work to be done. But this is sort of describing where my head is at right now. So I'm sure I went over, and I apologize. Thank you.
Thank you, Mark. So maybe we'll just circle back and let each one of the presenters sort of summarize, critique, and offer some of their insights in terms of how we move ahead in the future in this area.
Do you want me to start?
Certainly, John.
So I guess one thing I'd say, and this was somewhat echoed by the other presenters, is that from the hydraulic fracturing perspective, I think really what we need to be able to do is predict the variation of stresses between layers to get the. So let's make it simpler with the conventional example, the sand versus shale. If we get the gradient for the sand right, but we can't figure out how different the shales are, we're not answering a question. And so if you go back to the log-based method, often in practice, at least in my experience in talking to people, they literally just apply the nu over 1 minus nu component, maybe include pore pressure. And I can't argue against the assessment that the plausibility of how you get started in the elastic model is a difficult path, not a representative stress path, but I think the idea that variation between layers depends on the difference in property between layers, that is embodied in the elastic model. They have different Young's modulus, different Poisson's ratio. I think Mark would say that it's more important to know about the difference in frictional strength and difference in non-elastic properties, but the real world that we work in, I think, is a very data poor world typically, and so many of those examples I showed you have one data point, and that's the only site-specific information you have about the in situ stress, and so it's possible maybe the appropriate methods. My experience is that the appropriate methods would be different for different levels of data input. I mean, the data that Mark just showed was really incredibly compelling. But I'm always surprised at how successful we were with the simple idealized elastic model. But I can't argue about some of the need for non-elastic in many cases.
Thank you, John. Alexei, your thoughts, and maybe just follow on a little bit about what John brought up, is that in many cases data is very sparse, if you have any at all.
if any at all. Yeah.
How might you address this?
Well, I think, and that takes us away from a log-based stress estimate, is that we need to do more on the measurement side. And there are some developments, there are some commercial solutions available, like for example, wireline microfrac. So there is a disconnect between the depth resolution of models that we put, whether it's elastic-based, sonic-based, or VSR model. It's a high-frequency interpretation of stresses. And then when we calibrate, like Mark Zoback was showing, good calibration to defeats, but defeats are huge. The length dimensions are much bigger than variations we are looking at. If you pump defeats like 30 barrels, it's probably tens of meters in length, unless it's confined in a particular zone. So there is a disconnect, in my view, between calibration data depth resolution and the interpretation depth resolution that we have. So we need something like a more consistent wireline microfrac. There have been development of downhole strain gauge based tools, extensometer or pressure meter, as you call it. There are a couple of developments I'm not going to publicize, but people are working in Canada on at least two solutions I'm aware of. There have been attempts to do something with fiber optics and also extension packers. So it's not injection based, fluid injection based interpretations, but we need higher resolution in the data to calibrate these models, even when the premise for the model is right. But maybe very quickly, John's comments on to both speakers. Jon Olson, I would say that to me, there was always ambiguity whether we bring tectonic correction term to compensate for missing relaxation, this lithology-based component that I was discussing, and also which is part of the VSR model, or it's a true tectonic. And the only way that I think that tectonic is supported is when you get diverse stress, so sigma H max and sigma H mean are different. I think that requires external lateral loading. But then the question is, do we have accurate enough interpretation of sigma H max to estimate reasonably the tectonic component in our models? That would be question to Jon. And question to Mark would be, practically, I like more concept of using VSR model and starting from friction equilibrium and then adjusting it for amount of relaxation. The problem is that the input parameters in this model are less straightforward than those in Eaton's equation. We're now taking n parameter and time. So, okay, what time is reasonable and what creep component we should take. Do we need to take lab tests on for every fascia or lithological unit? So if you're in simple sand shale environment, it's somewhat easy. You just do limited amount of tests. If you're in a large intervals of shales, like we do in unconventionals, then you have a lot of variations, many fascias. So how reliable is input by using just correlation with Young modulus versus actually using lab data to specify that model? So those are two questions to speakers. I don't know if I have time to address them.
Thank you, Alexei.
Let me take a shot at answering Alexei's second question, because it's probably also in the minds of many of the listeners. I think it's simply remarkable that we have these wonderful data sets available, like HFTS1, for example, because they are documenting these large variations from depth to depth. And any model that's based on a single calibration point, is going to be, subject to whether you happen to be measuring stress in one of the high stress or low stress intervals. So calibration is always an issue, but I think it's important to work with the right conceptual model in mind. And in the Woodford data, we were given 4 defits, which I didn't show. And the operator said, well, we did 4 defits, but we only believe two of them because the other two are much too high. Well, it turns out those were the two in which the toe of the well was up in one of these viscoplastic, more higher clay intervals, in which case the stress was much too high compared to the well that was in that middle lithofacies. So I think just having the right model in mind when you look at this, but calibration is important, and but getting my sometimes it's easy to be glib, but we recover less than 10% of hydrocarbons from unconventional oil wells, and very 25% or so from gas wells. And I think we don't really understand where the fracks are going. And that was the purpose of that ERTEC paper, is to point out that the way in which stress is varying with depth has really first order impact on where the hydraulic fractures grow. And that, of course, is going to reflect production from every stage.
Thank you, Mark. So we have a number of audience questions, and we have 9 minutes.
Can I come in on, I'm sorry, how many minutes?
Oh, John, you have as much time as you want.
Well, I was just going to answer Alexei's question. Just so let me say this, I mean, I'm the elastic stress model guy. So let me say, in the context of when we're using that model, the fact that we don't have SH max information doesn't prevent you, I mean, again, in the context of the model, doesn't prevent you from calibrating the model. You calibrate the model with one data set or one data point, which gives you the tectonic strain in the plane strain model. And when you apply that strain, it modifies SH max and SH min differently because of the different directions, right? So you could test the accuracy against SH max, and that would be something that would be good to do, but it's SH max information is not needed for the calibration component in the context of how the model is derived. So the nice thing is it's really easy to do it. It's just whether you're precisely wrong or not. Okay.
So, well, we won't get to all the audience questions. So I'm just gonna pick two, probably. And the first is from Maricela Sanchez, and she has a question for you, Mark. And how do you feel about in situ pressure meter tests in which creep parameters holding pressure and measuring displacements with time could be used to support the VSR model?
Well, I think they'd be terrific. I think they're just very hard to do in practice, but it would be great to have some of those data as part of a calibration, for example. I mean, where would we have been in HFTS2 without all the fiber data, right? That really, told us a lot. When we started the work on VSR, well, we didn't just viscoplastic behavior of these, clay-rich rocks around 15 years ago. And for most of those 15 years, I was actually thinking we needed to have this, calibration of N. And of course, what Marcella is referring to would give us that. But, I think there are workarounds that make our, the methodology roughly right. But to be, precise as we can, the more information we had as possible. I just don't think it's going to be available very, very often. But if it's available in a few calibration experiments, that'll give us a chance to sort of advance the ball and improve the methodology.
And then I think maybe one final, although maybe we can slip into, is from Colin Sayers. Now, Colin says he wants to unmute his microphone, so we're gonna live dangerously here, and let him ask the panelists a question and maybe pose us a way forward.
Oh yeah, thank you. Can you hear me?
Yes.
Yeah, yes.
Yeah, so I think it was a great debate, and I wanted to thank all three speakers. That was wonderful. I just have three comments, and then I have a possible way forward. The first comment was to John in the Eaton type approach, where you introduce a term in the horizontal strains. One thing to note is that in the assumption of zero lateral strain, what is assumed is that the total horizontal strain is zero. Now, the total horizontal strain is a sum of the elastic, the plastic, the viscoelastic. So if you assume that that sum is 0, then you find that the elastic strain in Eaton is actually minus the plastic strain minus the viscoelastic strain. So that actually can be the so basically the Eaton type approach can include plasticity and viscoelasticity by recognizing that the 0 horizontal strain assumption basically is total strain rather than elastic strain. A comment to Alexei, which I thought was excellent. I like the unloading model, and it reminds me very much of the approach in solid mechanics, where you unload a spherical inclusion due to Eshelby. And I think that points a way forward. And I would very much like to see, if you could write that down, it points a possible way forward. And then the question to Mark, which also was an excellent talk as usual. The viscoelastic approach was pioneered by Norm Warpinski back in 1989, I think. And he said that what he showed was that you had to do an integral over all geological time, and he kind of gave up. I discussed it with him. He kind of gave up on it because you would never know the properties of the sediments over geological time to do that integral. So I very much appreciate the work of Mark and co-workers to simplify it. One thing I should say though is that it has great uncertainty in its application because, if you take the paper of Singh and Zoback, I think it was, they basically represent the vertical minus the minimum horizontal stress as a coefficient times the horizontal Young's modulus. And that coefficient was basically obtained by regression, assuming it was a function of V clay, TOC, V limestone, V quartz, gamma ray, density, resistivity, and porosity. And so, that is really, it's non-transferable. I mean, it's a fit to all those curves. And so it's not really predictive, I would say. Now, just to close, I would point out that a possible way forward is to turn the problem around. If you think of Eaton, you're predicting stresses from basically sonic measurements. If I am basically a rock physicist, and if you take a rock physics approach, what you would say is that the elastic moduli are functions of the stress. They're functions of porosity, clay content, stress, etc. And so rather than, an Eaton type approach, try and understand how the moduli measured by the sonic depend on stress. Now, this has been very successful for pore pressure prediction, for example. So in pore pressure prediction, we have rock physics-based models where the velocities are functions of pore pressure, and we're able to predict pore pressure from measured elastic moduli, and also from, seismic, going from seismic, borehole seismic to sonic. And so that is possible to invert those sonic velocities for stress. What I would say is it's important to measure sonic anisotropy, because what you want to do is to predict, as in the viscoelastic model, the difference between the vertical and the horizontal stress. And so, that requires an advanced sonic tool. So those are my comments.
Thank you. Thank you, Colin.
John, can I
Absolutely,
respond quickly?
Yeah.
Just 2 points, Colin. And you're quite right. Norm Warpinski pointed out this issue of viscoplastic processes affecting stresses. It turns out, and this is in one of the Sony and Zoback papers, we demonstrate that what's really important and what makes the parameterization easier in the work by Singh and Zoback is that it's the total strain that matters. You don't have to integrate over all of geologic time and take all of that in. We show different different loading paths through geologic time, and you basically come up with almost the same answer. And I disagree that the Singh and Zoback had no data analysis had no predictive power, because I think we spent more time in the paper on that than anything else. You throw away half the data and you try to predict the other half. And we took that question very seriously, because it could have been just a fit to this unusual data set with, I think it was 21 data points, which of course is like dying and going to heaven when you're dealing with these problems. But I do think it has predictive value, and so I think conceptually it has predictive value, and maybe that's the space we're going to be working in if we're completely without any calibration. But when you have better data, I think the predictability is greatly improved.
Thank you.
And with that, I'd like to thank our three panelists. Great presentations, really fantastic interaction, and I'd like to thank all of the participants online. And with that, we'll close things down. I apologize for those who didn't get their questions addressed. Thanks
you
very
all.
much, everyone.
Yeah, bye-bye.
Thanks, Jon, Alexei, and Mark.
Thank you.
Thank you.
Great